Hello, everyone. Welcome to Megger's monthly webinar series. We apologize for the delay. We were having some technical difficulties. Today's topic is advances in high current injection testing. And in this session, we'll be discussing, we'll actually cover the basic principles of primary current injection testing, focusing on the various different tests which constitute a typical test sequence. My name is Greg Valdez. I am the Marketing Communications Manager for Megger North America, and I will be acting as the moderator for today's presentation. I'll also be supporting you on any technical issues or questions for our presenter during the session. Now, on the right hand of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segments. You will receive a copy of the presentation afterwards and a link to the recorded session if you want to watch it again or share it with your colleagues. Remember, you can ask questions at any time, and I will interject them as we have time. Our presenter today is Robert Probst. He is an application engineer for our cable products. Robert is based out of our Dallas office here in Texas. Thank you for joining us, Robert.
Good morning, everybody. I have to apologize for the technical problems. The internet connection gave us a little bit of a headache here. So my name is Robert. I'm with the technical support group. We're based in Dallas. I'm covering mainly cable products, but also the high current stuff. With me today is also John Shanks. He's the product manager for all the relay products and the high current products, and he's also based in Dallas. And if I cannot answer a question, then I will, hand it over to John. He's with the company more than 25 years, and he is very experienced in the field of relay products and high current products. So the agenda for today, it will be 4 chapters, 4 topics, and the first one will be just a quick recap to refresh everybody on circuit breakers in general. I will go through that fairly quickly because it's not the main focus of the presentation, but I need to cover some of the basics so we're talking about the same things and everybody has a basic understanding about the pretty much the test object that we want to test here. The second topic will be why we're testing. The third one is dealing with an explanation what primary current injection is, what types of tests you're doing, and the fourth step is just the advances that have been made in the field. Now to the first topic, circuit breakers in general. So if you think about what kind of components you have in the power grid, you have transformers, you have generators, overhead lines, underground cables, but a very essential component is the circuit breaker or circuit breakers. And its role is pretty much, or its definition, it is a mechanical device. And I want to emphasize this because a lot of people forget about it. It does electrical switching, so its duty is electrical, but its construction and its way of functioning is mechanical. It is a mechanical device. It is the only mechanical device to break and make any current up to its own capacity, up to the highest fault currents that it can handle. And therefore, you cannot really get rid of the circuit breakers. It's indispensable. And to illustrate this, there's a lot of other switching devices in the grid. There's fuse disconnects and earth switches and whatnot. You could replace all of these theoretically with circuit breakers. That's not cost effective, but the circuit breaker can take care of all of these roles, while the other devices, fuse disconnects and so on, can only take on one of the duties, and they would fail, for instance, if you exceed their interrupting rating, or if you have a dead break switch, if you would open that under load. So the circuit breaker is really the universal apparatus to make and break. Its purpose is mainly to interrupt short circuit currents. That means the high currents. It's also there to isolate faulted parts within a more local power system, let's say an industrial site, but also isolating entire regions in the power grid, disconnecting control zones. It can execute any switching of any current under any condition up to its operating voltage. So that includes, for instance, especially on the type testing side, before you even get the finished product, all of the circuit breakers have to perform a lot of load switching, cap switching, shunt reactor switching. The circuit breakers are tested for critical current. Generator breakers especially are tested for out of phase. One of the test duties, one of the lines in the Table 1 test in C3709 is the short line fault. And you also do fault close testing. And the circuit breaker is also made to handle fault close. So what are the main requirements? And it sounds trivial, but it's pretty much essential to understand these functions to understand what tests you are doing with the circuit breaker. So in the closed position, of course, it should be a good conductor. Ideally, zero resistance, that's not possible. So to at least minimize the losses that you have in operation conditions. So the lower the contact resistance is, the less heat is being dissipated. In the open position, it should ideally be a perfect insulator, so there can be no flashover. Very important, the transition from the closed to the open position in particular, because that is the interruption, but also from the closed to the open to the closed position should be as fast as possible. And initially, when circuit breakers were introduced in the early 1900s, there was a big discussion if that is even an advantage, if circuit breakers will have an advantage. Well, nowadays with these fast mechanisms and the spring-loaded mechanisms and so on, they are way faster than any human could like mechanically switch. When the circuit breaker is operating, it should not cause transient overvoltages. And I don't know if that makes a difference. And when it interrupts the fault, it should withstand the fault. So a circuit breaker that is never being operated but then needs to be operated because there's a fault and it explodes, that's not really the purpose of the circuit breaker. It should withstand the fault it's designed for. Additional requirements, of course, it should be reliable. It should hold up in any aspect of its design over the entire lifespan. Very important, it must operate, and it must operate immediately, swiftly, even after it's sat there for, let's say, a decade or 2 decades. And also the climate should not have any influence, ideally, on its operation. Other additional requirements would be electrical endurance. Again, during the type testing, all of the circuit breakers have to go through a very high number of electrical operations to get an idea of the contact erosions and to meet minimum requirements there. And the mechanical endurance is pretty much also related to the electrical endurance, because most of the time you would also operate the mechanism. And the mechanism has to hold up also. Like only 3 or 4 operations is not good enough. The mechanism needs to hold up over its lifetime, and quite a few operations should be possible without breaking it. So when we're talking about circuit breaker testing, and that the circuit breaker is the last stand of protection and the key element of protection, of actually performing the duties of interruption and closing and load switching, what faults are there? What faults can we have in the grid? And I put all of them in the same diagram, so don't be confused. So the very classic fault that everybody thinks about is the 3-phase fault that you see it's indicated on the left. All 3 phases are shorted together. That is quite a rare fault, as I will show you in a second, but it can happen and is the most severe. Then you have a line-to-line or phase-to-phase fault. And then all the other faults are pretty much single-phase faults. So one of the phases are is either touching the earth or the neutral or both. There's also the scenario where you could have a face-to-face fault and then gets to ground. The difference between these faults is pretty much just what the grounding scheme of your network that determines what faults can develop and what is not so likely to happen. There's different ways to ground a network: high impedance, low impedance, resonance with compensation by Peterson coil. But in principle, a circuit breaker needs to be able to handle all of these faults. Now, statistics, and this is an average. I found a few different numbers, but if you average them, you will get to something like that. So 70% of the faults are face to neutral or face to ground faults. That is also just a result of the fact that 60% of the grid is pretty much in the low voltage level, and the typical fault in the low voltage network is a single phase fault. So these things have also to do with like the quantity, and that the transmission is like 10%, the medium voltage is 30%, and then the low voltage is 60 roughly. So then you have these nasty three-phase faults, very rare but very destructive. And then you have the face-to-face faults, which are somewhere in between. But the problem with those is that they can develop into three-phase faults, and then you have like the most destructive scenario again. Now, faults, and I will just go over that fairly quickly. The current wave shape can be symmetrical or it can be highly asymmetrical. That is determined pretty much by the X over R ratio of the faulted circuit. So the higher the X over R ratio is, which is the same as a low power factor or a low cosine phi, is the higher the peak currents can be, the asymmetrical currents. It is also depending on the closing angle. So you have two extreme cases. If you think about an open circuit scenario, open circuit voltage, a transformer or a generator is in no load condition, and you switch on or a fault happens, the best condition is on the peak of the voltage, because then the current will be fully symmetrical. If that happens close or at the zero crossing of the reference voltage, you will get maximum asymmetry. So that closing angle is also very important for the primary injection testing, and we will get to that a little bit later. And of course, it's determined if the fault is close to the generator or far from the generator. If it's far from the generator, there's the impedance of the line and the impedance of the transformer will bring the fault currents down, and the asymmetry is not as severe. Now, if we look at this just real quick, from the point of view of the generator, it has a subtransient reactance, the transient, and the synchronous. And when there is a fault or when you switch it on, you will have a DC component, and then all of these things will overlap, will superimpose, and you get an asymmetrical short circuit. And just in general, this is highly dangerous for generator circuit breakers. This is why there is a special test, a special type test for these breakers. They have to withstand a very long duration of fault current with no current zeros, because in a three-phase fault in the power plant, there won't be any current zeros, and you will get this very dangerous scenario. Now, before we go into the testing itself and the low voltage breakers, just in general, how can you classify circuit breakers? Circuit breaker is not the same as circuit breaker. There's this and that is that. So you can classify them by basic insulation level. That's a very classic way to do it. So everything below 1 kV AC or 1.5 kV DC is considered low voltage. Everything above is generally considered high voltage. Now, then in the high voltage world, there is these additional classification that people say medium voltage is typically considered to be up to 52 or 72.5. That depends on who you ask. And high voltage or transmission level is 110 kV and above. And then you would have sub-transmission level. Some people call 69 kV sub-transmission level. You can also classify the breakers by the way how they quench the arc when they switch or interrupt the current. There's air breakers, oil breakers, SF6 breakers, then more and more popular, the vacuum breakers, and then the movement away from SF6 to trying to find gas mixtures that have similar properties like SF6, but it's not SF6, so you have the SF6 nitrogen mixtures and then other compounds that are in development right now. Then you can classify, which is important for our understanding of low voltage breakers, by the method of how they interrupt the current and how the transient recovery voltage is controlled. So all the low voltage circuit breakers, because they're constructed in a certain way, are inherently current limiting. And I will explain that in a second. Especially the old air blast high voltage circuit breakers, they had pre-insertion resistors, and vacuum circuit breakers particularly are zero crossing circuit breakers, so they need zero crossings. The current has to go from one polarity to the other, and in that moment the interruption can take place. And all of these methods are pretty much defined by the construction of the circuit breaker and by the voltage level, because certain things are not applicable at certain voltage levels. Then a very classic classification is structural design. Pretty much very popular in the rest of the world, live tank circuit breakers, specifically Europe. This is pretty much the dominating circuit breaker technology, and why in North America, Canada, and the US, it is the dead tank design. You can classify them by motion. So below 245 kV, you have 3-pole operated breakers, and then you have single pole operated, individual pole operated IPO. And now, within this classification, the low voltage circuit breakers, that is pretty much a bubble in itself. It is circuit breakers still, but they're different from medium voltage circuit breakers and high voltage circuit breakers. And there's pretty much 4 different types. You have the airframe circuit breakers, then you have the insulated and molded case circuit breakers, and then you have the very small, the miniature circuit breakers, which are pretty much used in households as resettable fuses, for instance. If you have never seen a low voltage circuit breaker, I just pulled some images. So you have the molded case circuit breakers in the upper left, and then the bigger ones, the airframe circuit breakers. And a very essential difference between those types of breakers and the medium and high voltage breakers is that the low voltage breakers have a trip unit, which the medium and the high voltage circuit breakers have not, because there the function of the trip unit is taken care of by relays. And these trip units have curves, and I put one example on the right. So these curves look more or less the same, and this is the specific case for the low voltage circuit breakers. Then they come in different sizes, different manufacturers, ABB, Siemens, Eaton, and they can go up to 600 volts, 690 volts. Then they, of course, grow bigger in size as well, because you need the isolation distance. Now, when I said inherently current limiting, this is what I'm talking about. If you think about a fault in a system that is not protected, you would expect a so-called prospective short circuit current, which is indicated by this big sine wave. Now, with the circuit breaker in the circuit and with the right settings, the circuit breaker will clear that fault. And the result will be that there is a certain let-through, but is much smaller than the prospective current, and it is there for a much shorter amount of time. Also, molded case circuit breakers specifically typically do not need a zero crossing, so that interruption is done in less than a cycle, typically even half a cycle. Because of the mechanical construction of a molded case circuit breaker, they are only able to automatically trip. So they can sense the current, the fault current, and they can trip. The user or a technician or whoever has to go to the breaker after a trip to reset it and close it in again. Airframe circuit breakers are typically the same way, but there are also models that have a closed coil, like medium voltage circuit breakers, and can be remotely closed as well. Molded case circuit breakers are typically thermomagnetic, nowadays also with electronic trip units. Thermomagnetic means, as you can see in that picture on the bottom, the green portion is the magnetic part. It's a CT that is there to sense the high currents, and the yellow part is a bimetal component, and that bimetal takes care of the lower, more of an overload type fault. And then this third part that is highlighted here, that is the so-called D-ion chamber, or some people call it arc chute. That is a set of plates of a very specific design, and that is pretty much the place where the arc is being extinguished. And the way it's done is it has three functions. First of all, it splits the one arc that develops across the opening contacts into many smaller arcs. That way you create more foot points, because a typical arc has 2 foot points, one on the one side, one on the other side, and in between is the plasma column. And now you split that up, and on each side of the plate there is a new foot point. Now there is an interesting effect that at those foot points additional voltage drop is created, and that is mainly a function of the material. It's not a function of the current or anything else. So you add a lot of foot points and the voltage drops across these foot points. You also elongate the arc, and you at the same time cool the arc. And with these three effects, splitting or separation and creating more foot points, elongating the arc and cooling the arc will vanish within a few milliseconds, and the circuit is interrupted. Now, why are we testing? Why are we testing circuit breakers? Unfortunately, like any component in the network, in the grid, they can fail. They're often exposed to years and years of inactivity. I've personally seen breakers who have never been operated since they were installed. As I said, they are mechanical systems, so a lot of parts are interacting with each other, and if one component is not good, then the whole function of the system is in danger. And they have typical service lives of at least 20 to 40 years, like any other component in the power grid. So they need to be tested, because the situation 20 years later is not the one the circuit breaker was exposed to when it was commissioned. So now we have different tests for circuit breakers. We want to talk about primary injection, but what other tests would a service company or a utility do? Well, for the conductive path, you know, it's a resistance test. You can measure the contact resistance, typically with a DLRO, digital low resistance ohm meter. Very important is the electrical insulation. There you can either do a typical Megger test, an insulation resistance test, and or a high pot. So you can test line to load, all live parts to enclosure, opposite polarity, which means hot up B phase, ground A and C, and just make sure that the insulation, the dielectric withstand capabilities are still there. Then you can test the trip unit, just the trip unit by itself. That is called secondary injection. And then to test the actual operating mechanism, this is called primary current injection. And if you think about it, when I say operating mechanism, that's not entirely true, because at the same time, you will test the trip unit and the contacts. Because if there's a malfunction in the contact system, the test won't be successful. And if there's a problem in the trip unit, the test won't be successful. So with the primary injection, you're pretty much testing everything. You're testing the entire breaker. And this is why the primary current injection is the preferred test, much more preferred than just the secondary injection, because the secondary injection doesn't really tell you much. Yeah, well, the trip unit is good, but are the outputs that the trip unit generates, are they transmitted correctly, and are they picked up by the mechanism, and is the circuit breaker actually moving and actually doing the interruption? So the primary current injection is the only test where you can find out that. Problems. Why are we talking about testing circuit breakers, and what could be the danger? Well, if the circuit breaker fails to interrupt for whatever reason, it can be a disaster. People can get hurt or killed. For me personally, I would make it mandatory that every person that works in the power industry goes to a test lab and watches some of the interruptions and some of the testing that is being done during the type testing. Because once you see what happens when a circuit breaker interrupts or fails, there's no discussion about why are we testing and should we test. Nobody wants to be in front of a fireball and be killed by that. So a fail to interrupt can be a potential disaster, but the opposite is also quite harmful to businesses. This is more of a business point of view. If a circuit breaker would see an overcurrent condition that is to a certain extent tolerable, acceptable, but it trips right away because of false coordination or whatever, it can be very costly. Think about a chemical plant. Some of these processes needs days to be restarted, or some of the stuff that is made in a refinery that has to be in motion constantly. Once it's in rest, you will never be able to liquefy it again. So if you clear every single short duration fault, you can be in trouble because it can cost millions. Another application would be a conveyor belt, that it shuts down the entire production line because of a spurious or an incorrect trip. So it's also very important that the circuit breaker is not tripping too early. So quite the opposite from a high current fault. Now just really quick, the whole thing, the whole testing and verifying the curve and that the breaker is still true to its intended curve is selectivity or selective coordination. That means you have the different breakers and different levels in series, a main feeder, branches, and then a panel breaker, and depending on where the fault is, not all of these breakers should interrupt. Like the main feeder, the main breaker is the last you want to trip because down the line at the other end of the building there was a momentary fault. And to make sure that the breakers still act in accordance to the curve, so your selective coordination is still true, this is why we're testing. Now there's a few standards applicable. The NEMA AB4 is the most important. For the nuclear power plants, the NMAC Volume 3 is very important. And there's a few others where you can find guidelines and standards and requirements on low voltage circuit breakers and the maintenance and the testing of low voltage circuit breakers, especially NEMA AB4. Now, what are common failure modes? Well, pretty much it's Murphy's Law. It's a complex mechanical system, as we said, and what can go wrong probably will go wrong. So breakers can be used in the wrong application. They fail to trip. You rack them back in, for instance, airframe circuit breakers, and they should not be trip-free, and suddenly they're trip-free because some mechanical parts broke. You can have insulation failure, springs, contacts, everything that is moving or under stress, under mechanical tension, can fatigue and break. It can simply fail to withstand. That means it is okay, but then a fault happens, maybe a fault that is beyond the design, which technically should not happen, but it's, you know, it could because of wrong short circuit calculations, and the circuit breaker blows up because the fault was higher than its maximum capability, and age, corrosion, whatever. Parts then can, like the springs can fatigue. You can have cracked cases, deformed metal parts, so live parts can be exposed, and you lose your dielectric withstand capabilities because the distances, the clearances are not there anymore. The current sensors can be miswired. I personally have seen that quite a few times. Wires can be broken, and then the commands of the trip unit is not you know, correctly processed anymore. You can have loose connections that can be external connections, the cables at the poles, or internal connections can be loose. The set points for the long time pickup and so forth can be wrong, so wrong multiplier settings. For instance, somebody tested something or tested the breaker, changed the settings and forgot to put it back. The solid state devices, the electronic trip units themselves can be, components can go bad, transistors, integrated circuits can go bad, capacitors on those boards can go bad. They can be exposed to an overvoltage and be shot. They can be programmed incorrectly to the wrong application. People are doing maintenance, putting on the wrong lubricants, and everything now is kind of like gummed up, if you want to, or they use WD-40, a classic, which is not a lubricant, and introduce corrosion to the mechanical system. All of these things can happen. So now that we know what circuit breakers are and what can go wrong and why we're testing, so what is primary current injection? And as I said,
Robert.
Yes, Greg.
I'm sorry, I wanted to jump in with a quick question here from the audience before you move to the next section. You described different types of fault waveforms, i.e. asymmetric and symmetric.
Yes.
When tested with primary injection, what type of waveforms are used and why?
You will always use a symmetrical waveform, and this is even in the standard. You will find that in all the documents that I put up. It's specifically spelled out that you use symmetrical waveforms because you want to measure the actual trip times, and this asymmetry can lead to early or false trips, specifically on the instantaneous test. And to avoid that, the DC component needs to be eliminated. That's actually very important. It's a very good question. So you always use symmetrical waveforms. Well, now one could argue that on the long time test it doesn't really matter because there's so many cycles that this little asymmetry, if there is one in the beginning, doesn't matter. Technically that is true, but also for any test you should always eliminate the DC component, specifically for the instantaneous test, because it will be an at least an inconclusive or invalid test even. Any more questions, Greg?
No, sir.
Okay. So what is primary current injection? As I said, it's the only method to test and verify that the entire system, the system low voltage circuit breaker, works. That means all of the components work. And I spelled it out here a little bit more detailed. The mechanical parts, the operating mechanism, then the contacts. Of course, not just the main contacts. In a low voltage, like in an airframe circuit breaker, you also have specifically arcing contacts that applies, that it's the same, so any contact. The arc chutes, of course. The trip unit, very important, because that's kind of the brains of the circuit breaker, and that all the connections are good. And what is the main principle? Well, you connect a current source to the circuit breaker, and you run fault current, or let's say a determined test current, through the circuit breaker. And then you just simply watch. You sit back and watch if it trips or not. hopefully trips, and hopefully it trips not too fast and not too slow. So you run current through, this is one parameter, and then you measure time. So you start a clock and then you stop a clock. That's pretty much the basic principle. Fairly simple, but there's a lot of pitfalls to that. Now when we're saying curves, so this is a typical curve for a low voltage circuit breaker. It explains all the different things. Specifically for an airframe circuit breaker, molded case circuit breaker typically does not have a short time and typically does not have a ground fault. So you have a portion that is long time, short time, instantaneous, and as you can see, these curves are log-log curves always, so they are scaled in decades, and the x-axis, so to speak, is the current, and the y-axis is the time. Now I pulled some time current curves, as they called, out of a Siemens handbook, and I highlighted for molded case circuit breakers, I highlighted the two areas of interest. So on the left you can see the long time portion, and on the right there's the instantaneous portion. And as I said, an airframe circuit breaker would have a short time in between there and an additional set of curves for the ground fault, if it has a ground fault device. Now for each section you can assign a test, which is a long time test in one case and an instantaneous test. And in practical terms, for a practical application, the long time test takes care of the overload capabilities and the overload specifications of the breaker. And the instantaneous is to check the short circuit properties of the circuit breaker, that it is actually capable of interrupting the high faults with no time delay, while the long time test and the short time test typically have a delay to them. Now again, I pulled back this image from the molded case circuit breaker that was here cut in half, and you can see what section of the curve is, taken care of physically in the circuit breaker. So you see the long time, that is the bimetal portion, fairly low overcurrents for a long time before that element trips, and no time delay, high currents picked up with the CT and leading to an immediate operation of the circuit breaker. There are actually circuit breakers that can be in this portion of the curve for minutes, 10 minutes, 15 minutes. So it's not always seconds. Now, in general, what types of tests do you run? You do a long time test. If applicable, you do a short time test. As I said, that's mainly for airframe circuit breakers. You do an instantaneous test, and you do a ground fault test if you have a ground fault module. And the typical value is that you run the long time test at 3 times of the continuous current rating of the breaker, which is the same as the sensor rating. There's also a term that is called frame rating. You have to be careful with that. Frame rating means what manufacturers do is they build a certain circuit breaker, a certain module, and then you can equip this circuit breaker with different CTs, with different sensors, and they can have different ratings. So they have one mechanical design to accommodate different electrical duties. And also, this is why I put a slash there with long time pickup. Certain manufacturers have the tradition, for instance, GE, very unpleasant I have to say, that they don't give their settings and express their settings on the trip unit in sensor ratings. They do that in long time pickup multiples. So you know, for instance, the unit is a 1200 amp sensor, but then they have an additional setting saying long time pickup, and everything else, the short time pickup and the instantaneous, is in multiples of that long time. So it's an additional calculation you have to watch. The the majority of the breaker manufacturers, it just sticks with sensor rating. So they would say, my long time is 3 times my CT rating. Let's say if the breaker is, if it's a 400 amp sensor, you would do the test at 1200 amps. Then they have, if they have a short time setting, you would set the short time, and then 1.5 times of that you would do the test at. So if you have your short time pickup at, let's say, 2000 amps, for instance, you would run the short time test at 3000 at 1.5. You run the instantaneous test at the pickup value it's set to. There's also a little pitfall. Typically, you should do a test at below 80% of that to make sure that the instantaneous is not picking up too early. And if the unit has a ground fault test, a ground fault device, you set the test current also at 1.5 times of the ground fault setting. Again, some manufacturers express this as well in relationship to some other settings. So you have to be careful. Now, if you don't have a curve and you don't have any idea, you can always go into the NEMA AB4, and they have this reference table to give you a help, a rough indication, how many seconds at what current should a breaker hold if you don't have any other information. So this is a guideline. And they give you also guidelines. I took this directly from the standard. Also guidelines for tolerances. And there you can see non-adjustable. That's a typical molded case circuit breaker that doesn't even have a multiplier. 30 amps, 75 amps, 125 amps in that area. So you have a plus-minus range for your band. Now, when you do the test in the practical in the field, as a practical application, you have a lot of problems to face, and I've listed a few here. You have input power requirements. Then I will talk about the circuit impedance in detail, because this is a very common problem. You have the problem of current decay because of the heat that the test device is dissipating. You have the problem of the DC offset, which we already had the question about. I will explain that a little bit more. Then a big problem always in the field is to compare the actual results to the curves, and report generation, data storage, data management, trending is always a problem, as well as the size and the weight of the test equipment. So now input power requirements, I won't read all of that, you will get the presentation later. But just in general, primary current testers are no magic boxes. What comes out has to come in minus the losses. It's really that simple. So that means if you are limited in your input power, for instance, you have a very long extension cord and you don't get 120 volts or 240 volts or 480 volts in your tester, you only get 80%. Well, you cannot expect to get the maximum power out of the unit, because the necessary power does not come into the unit. So you have to make sure that you keep your voltage drops to the box as low as possible. That's not always possible in the field, I know, but you know, you have to be careful with that at least. Don't yell at the unit when it's not giving you the power and you're at the end of a 300-foot extension cord, because there is limitations to that. It's always better to go to a higher voltage if possible. So if the unit has a wide range input, and you have the 240 volts available, you will get more power out of the unit if you go to 240. Now, circuit impedance, very important. As I said, these testers are high current sources. That means they will regulate their voltage output to a value necessary to drive a constant current. That means if you hook up two very different breakers with different lengths for the leads and everything, and you tell the instrument to run 1000 amps, in one case you could measure 2.5 volts at the output, and in the other case 5 volts. The unit will regulate within its capabilities to compensate the burdening that it is exposed to by the test device. So it's a current source. That means the more impedance you have on the output, the more you load the equipment and the less output you may get in a real-world application. A typical way to counteract is to twist the cables, a very important technique, because if you think about this, if you take a look at this picture here with this 800 amp circuit breaker, if you wouldn't twist the leads, just imagine you would make a circle between the two terminals of the tester. You would really put a large area between the two conductors. Then, by physics, the area between the two conductors, the lead to the circuit breaker and the lead from the circuit breaker, that area is proportional to the impedance. It's called the inductive loop of the circuit. If you maximize that, you're pretty much killing the output of your unit. So you should always minimize the area between the two conductors, and the best way to do that is to twist them and only open them up as close to the circuit breaker as possible. Minimize the lengths. Sometimes that's not possible, but the closer you can get the tester to its actual connection point, the lower your losses will be, because the resistance of the leads is dominating in this application, since the contact resistance of the breaker is typically relatively small. Use multiple conductors in parallel. Classic technique, increase your cross-sectional area, and as I said, twist the leads, as shown in that image on the right. Convenience of testing. If you have special probes available, special means of connecting, you can dramatically speed up your testing, because you just have to touch one pole of the circuit breaker, the other one can be hooked up as a common, and you can go through multiple poles, multiple circuit breakers fairly quickly. A typical example is a gun probe. When we're talking about current requirements, as we just learned with the long time pickup and the instantaneous is typically set between 8 and 12 times the continuous current rating or the sensor rating. So you need a tester that is capable of putting out a current in the range of 3 times your continuous ratings for a long time, and a tester that is able to pulse a fairly high current, 10 times the rated current. If you need higher currents, use a bigger tester, and this is what I mean by one size does not fit all. There is simply no primary current injection test set that can test all of the breakers, that can go from a 1 amp miniature circuit breaker to a 6,300 amp airframe circuit breaker. Different power classes require different sizes, different test instruments. There's the approach of modular sources, so you put multiple testers in parallel if they allow that, so you can get more current out or more voltage if you have to overcome higher impedances. And if you have a multiple box approach, these boxes typically act in a master-slave mode. That means the user designates one tester as master, and that controls the others as slaves. High impedance test objects. Typically, the smaller the size of the circuit breaker, the higher the impedance, the more driving voltage you need. Then you need means of seriesing the output of your testers if it has multiple outputs, or if you have multiple testers. But in general, the smaller the circuit breaker is, the higher the voltage that you need to drive the current. A challenge is always adjusting the currents, and all of the classic testers, before we come to the next, to the last topic, to the advances, all of the classic testers, doesn't matter from what manufacturer, they have a variac and they have a transformer. That variac is feeding into the transformer, and you have two different means of adjusting. You have a coarse adjustment, which you see on the left, different stages, a coarse select, and then you have a variac on the right that gives you the fine adjustment within a stage. The way you use that equipment specifically for long time and instantaneous testing is you put the unit into what's called the pulse mode, so it's just injecting a few cycles of current so you don't heat up the breaker, and then you find the settings for your long time test. You put the unit into the maintain mode, so it's outputting continuous current, and you run your test. For the instantaneous test, you start fairly low, and you just go up on the variac, and you ramp up. You increase the current that you're putting out during these pulses until you are in the area of the in the region of the instantaneous pickup, and hopefully the circuit breaker trips. That also means, because these this approach, this classic setup with the variac and the transformer, is relative, so that you will see there's no voltage or anything, it's just percentage, 10, 20%, and then the red numbers, because this one is a buck boost, 100%, 80%, and so forth. If you hook up a different breaker, specifically if you change also lead size or lead length, the same setting will give you a different current. So for each circuit breaker, if you're not testing similar breakers, you always have to repeat this kind of adjustment, because your inductive loop is your impedance, your burdening of the source is different, so the same relative setting will give you a different current. So this can be very time consuming if you have to test a lot of different breakers. Another thing is the current decay is a problem. If you have breakers that can hold faults for a long time, 100 seconds or even in the minutes, your leads will heat up. On manual testers, on these classic testers, the user has to compensate for that manually. So you have to adjust that variac to make sure after 4 minutes or whatever you still have the same current. So it would be really nice to have testers that have an automatic regulation, so you don't have to worry about this as a user. So the unit is doing the regulation to the right current. Another thing is the DC component. The question already came, what waveform do you use? You always want to use symmetrical waveforms. So that means you have to take care of the DC offsets. There is no tester on the market, no classic tester, that can do that fully automated. There's means for adjustment, but the user always have to take care of that. What you have to do is the device that actually makes the current, closes the circuit, the gating device, you have to adjust the firing angle. And the way you do that, your current meter has to be able to measure true RMS, and it has to be able to measure what's called peak divided by square root of 2. On a symmetrical waveform, these two numbers are the same. If you measure the true RMS and you measure the peak and divide the peak by root 2, that should be the same number. If you have a fairly asymmetrical waveform, these two values are not the same anymore. So on a classic tester, you have to do 2 injections before you start doing any testing. You have to verify that the numbers are at least very close, and you verify that there is no DC component. If there is a significant difference, then you have to start adjusting your firing angle and do 2 more injections, or even depending on how close you get. And you have to keep doing that until you find the minimum between the 2 values. It's a very time consuming process, and but the standards call for it to be done. No asymmetrical component. So it would be very nice to have a tester that can actually measure all of that, and have a source that can be turned on in a way that the DC offset is fully compensated. Now, the next thing is comparing the trip times to the curves, also very time consuming. First of all, you need the curve. Second of all, you need to be able to read the curve. And this is actually, even though it doesn't look like it, it's a kind of a complicated one because it has all kinds of adjustments and exceptions to it. And this is, by the way, for an airframe breaker. So you have the long time, the short time delay, and then the instantaneous. So then you have to be able to read the curve. Then you have to be able to put your results into the curve to compare it accurately to determine was that a good test or not. So again, it would be very nice to have something that does that for you, that knows the curve, or where you can select the curve, where all the test values, the results, are put into and compared with the curve at the same time. This gets particularly difficult for airframe breakers, and I pulled one result here. You can see on the right, this is a fairly complicated curve, and here you can see if this function is realized in the software, you're making sure that you don't test to the wrong curve, or you interpreting the wrong curve. Because what the manufacturers are doing, the manufacturers are, let's say, very efficient. Let's not call it lazy, let's call it efficient. They put all of the settings into one curve, as you can see, and then they give you notes and descriptions. So this curve describes all of the settings on that circuit breaker. Well, you have to find out on what actual curve you're operating, which is most likely not drawn here. They only give you the extremes, the minimum and the maximum, and then enough information so the user has to extrapolate. Well, if you have a software that has everything in it, the complete curve, and you can choose what settings you have, you see the curve you're actually testing, and you are comparing to the actual curve that you are testing to. And if you would have a software that can do that for you, the next step would be to generate an automatic report that has the curve in there, all the values, and because it knows the min-max values, it can give you a comparison in the style of pass-fail right away. And of course, size and weight of the test device are critical. Transformers, especially for higher currents, they get very big, very heavy. The variacs have to be sized accordingly. So testers, if you use the classic approach, the testers can be very large and very heavy. And then it's not a question of portability anymore. Those testers are typically just transportable, but you cannot pick them up anymore. They weigh a few hundred pounds and are pretty big. But they can test circuit breakers that smaller units cannot. But it is possible that even those large testers can be shrunk by using a more modern approach. And this is pretty much the last topic. And whatever I showed you just for the challenges, this is pretty much what these new testers, these automated test sets, are capable of doing. One example would be this, a fairly small box. And what is happening with these new designs is that instead of the classic approach with gating device, variac, and transformer, you use a modern approach with semiconductor technology, power electronics. And you create a controllable, regulated power source with the power electronics. And that leads to an immediate effect of downsizing, since you get more watts per kilogram out of power electronics. So the test set will get smaller. I mean, test sets comparable in the same power class, one based on semiconductor technology, will be smaller, will be able to drive higher currents, and will be lighter. It won't be light, but it will be much lighter than the classic tester. You have the ability immediately to have a regulated output, because there must be a feedback loop controlling that the output source, the power electronics. You can get rid of the variac. You can have an output that is programmable. So you just tell a software, this is the current I want. This unit will run a pretest to measure the impedance, to measure phase shifts, to calculate how the power electronics components have to be controlled to immediately get to the right output current during the first half cycle. So there's no ramping up to the right current, 5 cycles or 10 cycles, what some of these old testers need. There's no inrush or anything. The DC component can be eliminated because of the measurements these testers are doing. They adjust the current make to a symmetrical condition. They are fully software controlled, as you can see. There is no variac anymore, no display, nothing, just the emergency off. So you can have an industrial grade computer, for instance, or a laptop. In the software built in, you can have a huge database of time current curves. So you can have the curve right there. There's no guessing, and you can work with the actual curve in the software. No manual comparison necessary anymore. And you can have an automated report generation. So pretty much all the hardships and challenges, except maybe the impedance and the actual power class, all of the pitfalls that you can have with high current testing can be addressed by the latest advances in the design of the high current test sets. Now, to come to an end, because it's already an hour, just as a summary, primary testing, as I said, it's the only test that really stresses and puts the entire circuit breaker up to the challenge. There's no way to achieve that with the secondary injection. Primary current injection testing is essential in the whole low voltage circuit breaker maintenance scheme. So if you do maintenance on your breakers, when you just to determine if they need maintenance, primary injection testing is the tool to do that, aside from DLRO and measuring or hypotting. And also, when you did maintenance on the breaker and you think the breaker is in a good condition, you should do another primary injection testing to make sure that the S left condition is now optimal. As I just introduced with these new test sets, the methods of doing the testing will change drastically because the software will introduce a high degree of automation, aside from the benefits that just by going to a semiconductor design that size and weight are reduced. Some of these testers can be taken on an airplane without any problem. In essence, it's all about time saving and the quality of results. So with the software approach, and that the computer is doing the assessment, because it's just comparing numbers, and computers are very good with that, you will save a lot of time since you have the curve, the computer is supporting you, the software is supporting you, and it's also increasing the accuracy since you don't have to do a manual reading on a maybe bad printed copy of your curve. The test results will be much more reliable, and the repeatability will be dramatically increased, that it doesn't matter what technician is doing the test, and it doesn't matter if one has glasses or the other one doesn't, or all of these factors that can, influence just the reading of a curve, of a paper curve. All of that will go away with the software because the software is taking care of that. Now, this is pretty much it for the primary testing. Just from the Megger point of view, just fairly quick, there's a vast amount of testers of different power classes. As I said, there's not one size fits all. So the SPI is for smaller circuit breakers, 200, 225 amps and below. So perfect for molded case circuit breakers. While the other end of the spectrum is the DDA 6000, which can output 60,000 amps. So you can test 6,000 amp airframe circuit breaker. there's test sets in between the Odin or the DDA 3000. Then we have two box solutions for circuit breakers up to 500 amps, the CB845 or the Ingvar, and also for oil reclosers, for oil circuit reclosers, there are a high current test set to do actual recloser testing, but that's a different topic. Any questions? I think we're through with the presentations, and Greg will open the Q&A session. And what I want to make sure is that I want to mention that, first of all, the contact information. I will go back to that slide in a second. In a few weeks, there will be another webinar. My colleague Mohit Sharma will present on introduction to breaker failure protection. And right now, I want to make sure that everybody is aware of that we have a sale, an offer. If you buy one DDA 6000, you will get the next generation test set for the molded case circuit breakers for free. So as you can see, this is valid through October 31st. So you will find this advertisement on our webpage.
All right, thank you, Robert. And as you mentioned before, based on the feedback from last year's sessions, we're going to extend the presentation to include our Q&A session and make sure we try to get to all your questions. So if you have any questions, please submit them into the Q&A box now. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve our future webinars. A copy of this presentation will be emailed to you in the next few days. A recording of this session will be available on our website at megger.com/webinars in the next few weeks. So for now, let's go ahead and get moving on the questions. All right, Robert, here is the first one. What is the difference between primary injection and secondary injection circuit breaker testing?
Well, the primary injection testing is you run the current through the poles of the circuit breaker, and all of the components have to work together. They have to be functional to actually make the circuit breaker trip. While it's a secondary injection, you just test the trip unit by itself. You can even do that with the trip unit disassembled from the circuit breaker. So this is just the trip unit.
Okay. What about using high current injection testing to test differential protection elements?
You want to answer that, John? In principle, it's possible. You would do it the same way. You would inject, since primary injection testing is also single-phase injection, so you can actually generate differential currents and prove that your protection scheme is working. Another application would be just to check the entire protection scheme, not just the differential that applies to everything. You inject current through the primary of the CT, which is the bus, and then the CT will pick up. It will feed that into the relay. The relay hopefully has the right settings and will trip the circuit breaker. So actually in the medium voltage world, primary injection is also used. It's not just for the low voltage applications. I just had to focus the presentation because of the time restrictions. But it is also a very common method in the medium voltage world to test the entire system, CT relay circuit breaker. You want to add to that, John?
Only to add to that, in differential protection schemes, as an example, transformer differential protection schemes, you're looking for faults inside the zone of protection. This can be handled by either increasing the amount of current in the primary and decreasing secondary, but those are run with slope tests. To do that is either single phase or polyphase. That means you need multiple boxes to do this. In addition, specifically for transformer protection, there's a common test called harmonic restraint test, which validates that the protection scheme will not trip on transformer energization. This is all fairly complex stuff, typically not handled via primary injection because of the complexity of slope test, harmonic restraint test, through fault test. Those are typically handled via relay protection schemes. So yes, as Robert said, it can be done, but it can get costly and sometimes beyond the capabilities of primary injection systems. Thus, relay protection schemes and relay test sets are used to validate those particular elements.
All right. The next question is, can you please explain the safety issue of injecting 10 kiloamps in a live substation? The risk of personal damages if the breaker fails are very high. Is the high current injection test restricted to laboratories and to factory tests?
No, this is a typical offline test. So you do not do that injection while the equipment is energized. So this is a test that you do as part of your maintenance approach, of your maintenance program. So you take a substation, a feeder, whatever, out of service, and then when it's de-energized, you inject the current through the test device. So it's definitely not limited to the labs, even though in the labs you do that. It's part of the type testing when you do trip outs after the short circuit testing evaluations. But it's a very common maintenance test, a routine test on circuit breakers that are in the panel. Some people, they have the luxury of taking the circuit breakers out and get them to the shop and test them like on a bench in a shop environment. But it's not limited to labs. But it is an offline test. You cannot do that when this equipment is energized.
If I can also add to that, running a 10 Ka test in a primary injection method, these primary injection boxes run at a low voltage output. The type test that Robert's referring to, which is done in the lab, is done at full voltage, full compliance current, and full compliance voltage. So that is dangerous, and can be destructive. So the primary injection test sets that Robert's talking to typically run lower voltages, typically less than 30 volts. So running a 10 Ka test, you are dramatically mitigating safety constraints or electrical safeties for sure, because your voltage class is so much less.
Yeah, just to add to this, I think I have forgotten to mention this actually. John is completely right. What you do is you want to do a field test. You want to do a test in the real world, so you don't have these large laboratory capabilities available. Then you have pretty much two options. If you have a source of limited power, you can either generate very high voltage and very low, and then the current is very low because your power is restricted. Then we're talking about insulation testing. That is a high voltage test at very low voltage. And the opposite is pretty much primary injection. There, you transform the voltage down and transform the current up to very high currents. And as John said, less than 30 volts. A lot of testers are 6 volts, 12 volts, 15 volts in that range. So you could, I mean, don't do it, but technically you could touch that. You can run 10 Ka, you can touch it, and it won't hurt you. It is low voltage, high current. That's the trade-off. And this is why the burdening of the source that I tried to explain with the circuit impedance is such an important thing, because your output voltage is 6 volts. If you consume 5 volts of that just because of leads and inductive loop and voltage drop, there's not much capacity left to drive a high current through that load.
All right, thank you. The next question is, does the use of primary injection testing reduce the life of the breaker?
Well, if it's done correctly, no. But of course, it's stress. So you just have to make sure that you apply the right currents you know, that the times are right, that you don't overstress it, and then it should be it should not be damaging or dramatically reducing the life of the circuit breaker. As I said, the circuit breakers itself, they should be, and they are designed to hold, to withstand mechanical endurance, electrical endurance, much more than the actual protection engineer or substation engineer wants to see during its lifespan. I mean, I worked in the test lab before, in a high-power test lab, and some of these breakers are exposed to 2,000 mechanical operations or more, or 2,000 electrical operations and more. They should never see that in the field, especially under fault interruption conditions. So in principle, the design is made to last well longer than the life expectancy. And if you do the primary injection testing correctly, there should not be significant contact erosion, and there should not be a dramatic impact on the mechanism. And the other thing is, since it's a low voltage test, again, the interruption is done at the fault current, but not at full voltage. And that changes the properties of the arc. So it's not a full, it's not an interruption under full stress.
The next question is, does the standard tell how often primary injection tests should be done?
None of the standards at this stage have a recommended time for test. This is typically decided for by the user and the criticality of the circuit. Some circuits are fairly critical depending on where they are, and for that reason they are tested and validated more often. Some circuits are less critical, and time may be extended for validation of correct operation. But nothing in any standard has a time fixed limit on it.
Yeah, I know from field experience that certain circuit breakers and certain utilities are testing important circuits every year, or even the manufacturer requires it, special applications, or it's DC, so primary injection also applies to DC. And sometimes these breakers are tested every year. Sometimes the time is extended, as John said. But that is to be decided by the user. You have to come up as a user with the test procedure, and you have to validate and pretty much defend that procedure, and you have to justify it. But it's up to the user.
Okay, the next question is, to lower impedance of connecting cables, do multiple parallel cables get twisted only, or are all conductors twisted?
Well, the parallel paths, that is not necessary. Important is that the area between the two, if you want to see it as legs of the circuit, even though it's not the right, like you have a set of leads that goes from the test set to the circuit breaker. Then the circuit breaker itself is like a burden on the source. It's an impedance, mainly resistive. And then you have the return. And it's important to minimize the area between those two runs. That is important. That is really what guarantees that the source is giving you the expected output capability, and that you're not killing the output by introducing a dramatically large impedance.
All right, the next question is, when testing with high current or primary injection, the breaker gets hot. This increases the breaker resistance. How does the primary injection test set compensate for this problem?
Well, the compensation is that you let it cool down. There's actually requirements in those standards that you test one pole, and this is specifically true for molded case circuit breakers, since if you think about the construction of it, the mold, it is a bad heat sink. So if you run a long time test and it's one of these breakers that can needs a long time to trip, you introduce and you dissipate a lot of heat. That is correct. And that heat, because the enclosure is a bad heat sink, will be trapped inside the breaker. so you have to let it cool down. You also have to make sure that you do the current adjustment process, that you do it the right way, so you don't start running at a continuous output and trying to find the right current. You pulse it first with very short pulses, typically 5 cycles is a good number, to actually adjust to the right current, and then you run it. And then you let it cool down. Another way of addressing these things, and that really depends on the application, some customers, they work around that. They have so many breakers to test in a panel that they start on, let's say, breaker 1 A phase, then they go breaker 2 A phase, breaker 3 A phase, and so forth. When they come back from the other end to the first breaker, it's already cooled down enough to start at B phase. So there is ways to work around that. But in general, yes, the heat is a problem and has to be managed. So you cannot just run through all of these tests quickly. You have to give it time to cool down, to reset pretty much.
I'd like to add to that in the fact that the breakers do heat, as Robert's mentioned, and testing in the standards do call for if cool down time when testing adjacent phases. Therefore, it is commonly practiced as test A phase, C phase, come back to B. In addition, the other thing Robert mentioned is the control of the current while testing, while these breakers heat. In typical primary injection systems that existed for many years, it was up to the user to maintain that current value during the test. As Robert mentioned earlier, you want to keep a symmetrical waveform. This means you don't want the waveform decaying as the sample heats. It was up to the user to manually adjust the test set to maintain that current value. Now, with automated test sets, there's digital feedback loops, PLL loops, where the user can set a current value, whatever the test value is, and the automated sets will now take that over for you and remove that burden from the user. So there's quite a bit of technology moving forward in time, taking some of the problems of this test and heating problem off the user.
All right, thank you guys. It is now 11:30. We're going to go ahead and end the webinar now. We do have a few more questions that are more equipment related, and we're going to go ahead and answer those one-on-one with the individuals who submitted them. But for now, this will conclude the Q&A session of the webinar. And again, any questions that are left will be answered with the individuals who submitted them. Again, you will be receiving a copy of the presentation via PDF form, and the recording of the webinar will be online as well within 2 weeks. Thank you all, and thank you, Robert and John Shanks as well. Have a good day.
Thank you. See you.
Thank you. Have a good day.